about some of the things on our agenda. So, some people had some questions about the assignments, the assessments. So let's go through those. You all had a go at working on your assessments yesterday, Monday. Okay, so you know what's required of you at this stage. I had a couple of questions about exactly some implementational things about the assessment. So let's take those in order. Some people were wondering in the, for example, in the probability assignment, which I think is what everybody was working on, where you allowed use the inbuilt random number generators in MATLAB. My answer to that is I would rather you didn't, for two reasons. Making your own one is very, very simple. And in fact, you can use the one that we made in class last Friday. It's only about 5 or 6 lines of code. It's very easy to write up. If you have any trouble making your own random number generator, let me know. I'll show you how to do it. The hard part of that assignment, or that part of your assignment, isn't making the random number generator, it's using the random number generator. So making the random number generator is pretty trivial. It's using it to do various things. Okay? So, after mic here, there's some people in the AM. So I would rather you did that. There are some random number generators built into MATLAB. You will find if you look at the MATLAB code for those that they are built upon similar algorithms to what we're discussing. So you can download the .m files and have a look, so you can understand what the MATLAB ones are doing. So by all means, use the MATLAB ones when you're developing the code and explore them and try and understand how to use them. But I would rather you made your own LCG codes if possible. Okay? So ultimately, substitute your own random number generator in. Again, it's only about 5 or 6 lines of code. If you need help, let us know. Some people asking about the game of poker. I knew I shouldn't have set this assignment to some students to do some smart alecky queries. Some people wondering about what kind of rules of poker we're assuming here. Is it Texas Hold'em? Is it Chicago Stud? Is it whatever various online variations that you guys play? I don't know. What I had intended was very simple. You take 52 cards. You use your random number generator to, which in a second, Palab, I see you have a query there. You make your random number generator pick 5 cards at random, and of those 5 cards you see, do you have a pair, do you have a royal flush, do you have 3 of a kind, etc. Okay, so we're not trying to make a poker simulator. You're not supposed to make 4 different hands and bets and swap cards and do all that kind of stuff. It's simply the first 5 cards you get, do you have a pair, do you have 3 of a kind, etc. Count the number of occurrences. You do get these special hands against the overall total of hands that you deal and work out the probabilities. Okay. In addition, you can go to a site like Wikipedia, and there's a very useful site which gives you the probability of the various hands of poker arising. It shows you how to do it using combinatorial mathematics, all the various combinations of so many pairs and 3 of a kind, etc. And that will actually give you the actual exact probabilities. Okay, so you can use that as a reference, and you can use that to test your code. If you make 1,000,000 hands of poker, and you work out the probability of getting a royal flush or whatever other kind of random hand you're interested in, you can compare it against the Wikipedia page and see how you get on. Okay, see do you get the same probabilities. Okay, so any queries about that? People happy enough what you have to do? How about you anyway? Pala, have you have a question there, do you?
Yes, Connor. Just a quick question. Like, I was looking on Monty Hall yesterday, like me, Connor, and Ben, we were working together. Is that the same random generator we are using twice? Because initially we have to you select one door from like 1, 2, and 3, and then second time you have only picking up two doors, so 1 and 2. Is it the same random generator you're going to use again and again, or you have to create 2 different ones?
For the Monty Hall problem, so let's just remind ourselves what the Monty Hall problem is all about. The Monty Hall problem references a game show in the United States back in the 1950s, which culminated in this piece of hokum where the person who had won their way through would be faced with 3 doors. Behind one door was a car, and behind the other 2 doors was a booby trap. It was a goat. And obviously the person wanted to, you assume the person wanted to win the car and not a goat, but assuming that was what they wanted, they would pick a door at random. So at that stage they have a 1 in 3 chance of getting the car. There's 3 doors, they pick one door, the chances are 1 in 3 they're going to win the car. Now what made the Monty Hall problem interesting was because the rules or the way they did the game was that upon choosing one of the doors, there are 2 doors left over. Okay? And of those 2 doors that are left over, there is at least 1 goat behind one of the 2 doors left over. So the person, the game show host, whose name was Monty Hall, he would open one of the 2 remaining doors to reveal a goat and heighten the tension. He'd say, well, okay, you picked a door. There's definitely a goat behind some other door, leaving 2 doors at this stage. Okay? And the crux of the problem, the crux of the misunderstanding occurs because at this point in the game, the person was allowed to change their mind if they wanted to. Having seen the location of one of the goats, the person could now either stick with their original choice or they could move it to the other unopened door. Now, why this caused a controversy was because one would think, well, is there any advantage in moving? Surely, the guy's opened the door, he's shown us a goat, he could always do that, there's always 1 goat for him to show at least. So a lot of people, when they think about this problem, they think, well, at this point, it's 50-50 whether the car is behind the original choice or whether it's behind this other door. So there's no great advantage in changing. It's 50-50 is what a lot of people think. But you can show, and maybe we'll show it at some stage, I'll write out a proof of this, that in actual fact, it is worth your while to always change at this point. Okay? Because when the Monty Hall, when he opens that door to reveal a goat, he tells you something. He tells you something not about your original choice, but he tells you something about the other door that he chose not to open. He could have opened that other door, but he didn't. He chose to open the 3rd door to reveal the goat. So he's given you some information, and that information he's given you tells you nothing about your original choice, but does tell you something about that other door. And you can think about it in terms of probabilities as follows. The original situation is the probability is 1/3, 1/3, 1/3. Monty Hall opens a door to reveal a goat. Now the probability of a car being behind that door is now 0. So the 1/3 probability that was there gets transferred entirely to the other door. So the probabilities actually become 1/3 for the original choice and 2/3 for this other door. And people, the mistake people make is they think when he opens the door, the probability of the 1/3 that was there gets spread equally over the 2 remaining doors, your original choice and the other door to become 50-50. It doesn't. That 1/3 probability that dissipates as soon as he opens it to reveal a goat does not get spread equally. It goes entirely to the other door. I've lost my connection for some reason. And you can show that using Bayes' theorem. You guys would have studied Bayes' theorem and signals last year. So I'll write out a PDF and show you. Okay. Story behind it. So, Palab's question was, well, how do we simulate that? Well, what I would suggest you do to simulate it is you make a random number generator which gives maybe 3 numbers, 1 to it. And depending what number it gives, that is where the car is. And in every go of the game, maybe you have decided in advance you're going to pick door number 1. And you can play it 2 ways. You decide that one strategy, you'll investigate one strategy whereby you always stick, you never change your mind. We'll make maybe 10,000 iterations or 10,000 variants of this game, to play it 10,000 times. Each time randomly assign a car behind one of the 3 doors. There's a little bit of MATLAB code to work out what happens if you stick. Would you win the car? You'll find out if you win the car 1 in 3 times that way. Then a bit of MATLAB code to play the other strategy. Play 10,000 versions of the game where you make at every iteration of the game or every variant of the game, you pick a random number between 1 and 3 to locate the car between 1 and 3. You have decided in advance you're going to pick one of these 3 doors, but then what you do is you change your mind, okay, and pick the other door that's left over. Okay? Write some MATLAB code to simulate that. And in that variation of the game, you do it 10,000 times, you should see that you win 2/3 of the time rather than 1/3. So what I suggest you do is, in advance, you say, I'm always going to have an initial guess in door number 1, perhaps. Pretty easy. Do 10,000 variations where the card gets randomly assigned behind door 1, 2, or 3. Follow the logic of what happens for strategy A, where you stick. Count the number of times you ultimately win, following that logic. Follow the strategy for strategy number 2, whereby you always change. Follow the times you win using that strategy. And you should find that it breaks down 2/3, 1/3. Strategy 2 is the better. Okay. Does that help you? I muted Pala.
Yes.
There you are.
Yes, that helps. But my question was, we are still using the same random generator for both the case to select the doors, right? Only one random generator, right? We do not have to create 2.
I mean, the selection of the doors is
1, 2, and 3. That's it.
Doesn't really matter. I mean, let's play out a scenario. Say you pick. Say there's 3 doors, and you pick door number 1, and the car happens to be behind door number 1. Well, then Monty Hall, the presenter, can open up door number 2 or door number 3. It doesn't really matter because both of them are goats. You can open either one of them. Okay. Okay. So it doesn't matter which one he picks, and in fact, you don't even have to choose that randomly. You can just say, always pick door number 2 in that case. If instead there's door number 1, 2, and 3, and you pick number 1, and the car is not behind number 1. Say the car is behind number 2. Well, then Monty Hall, he has to open a door, either door number 2 or door number 3, because you picked number 1. He can't open number 2 because there's a car behind it. So he is forced, therefore, to open number 3. So there's no randomness there in that case. He is compelled to open door number 3. He doesn't have a choice. He has to open one of the doors, either 2 or 3. He can't open 2 because there's a car behind it. So he's forced to open 3. So there's no actual randomness in that part of the game. It's quite predetermined which door he has to open. Okay?
Yeah.
But the only randomness to be worked out in all this is where the car is originally. Okay, so the car is either behind door number 1, 2, or 3, and it's a 1 in 3 chance of each. And you can simply make a random number generator to achieve that. Okay.
Okay.
Good.
Yeah.
Okay.
I'll try to do that, and if I need help, I'll contact you back in case.
We can talk on Friday again. For any YM students, if you want to talk to me, I'm available on Friday mornings. I think I said 12 o'clock. Send me an email and we can talk by phone or by Skype if you need to discuss your assignment, okay?
Thank you.
That's all that stuff. Let's a few more announcements. Let me see what we're doing here now. Bear with me for a second. I'm just going to change computers very briefly. So I'm going to change over to my other laptop here, which now becomes the presenter. And let's see what we can do here. Okay, so anyway, I'm just changing laptops here. I'm going to present on a different laptop just for a second. Okay, so you should start seeing some desktop sharing now in a second. What I want to do is just go to the website, this course, and have a quick look and see where we are in that, see what's available for download, make sure everyone's aware of it. So here's the website. Okay, so hopefully everybody has found the website at this stage. The website has various bits and pieces on it. You can get computation course notes. I shall be endeavoring to get the notes for the lectures up prior to the actual lectures taking place. That way you can download them, you can print them out, and that way you can scribble on them when I'm talking. So Didn't make it much advanced today, but I will try and get them up in advance if I can. And so now there's 3 sections up there. Their introduction, section 7 we did last week, and this is what we'll be doing today and Friday, iterative finding groups, okay? In addition, you can find here, last Friday we had a talk about random number generation, and we made a random number generator. In fact, we made a little random music generator which played 1 to 32 songs in a random fashion, and we had a music quiz, okay? So that code is now there for you to download and study if you wish. If you want to as well, I have made the 32 musical snippets available in a zip file as well. Download those 32 little 10-second WAV files, okay? And that makes it easy. The MATLAB code links to these, so you need 32 little bits of WAV to play. So put this in a folder called snippets, put it at a higher level to where the MATLAB code is running. So that's there for you to download and play with. Right. Hello. The audio. Oh yes, that's a good question. I'll show you that for the DCU students. Okay. So the question is, where can people download or access the recorded lectures? And I'll show the NUIM students know where that is, but I'll show the DCU students that now in a second. And in addition, back here, you have information about the computation project. Assignment details available here. Everybody has an assignment at this stage. Here's all the teams, group numbers, group 1 down as far as about 20 groups this year. It's great. Lots of team information. So make sure that your team is here. Okay, make sure that if you sent me an email, I think I've captured all the different teams and I put them all up here for people to see. So make sure that your team is there. Okay, if your team isn't there, send me an email. I asked, or I suggested you might want to give me a group name. 1 team so far has given me a group name, so thank you very much for that. Group 2 would like to be known as Justin for Taoiseach. French students are looking at that and wondering what the hell is that all about. So I'll tell you, we'll have a brief little politics lesson now for 2 minutes to explain the choice of this group. But could everybody else please send me a group name as well, okay? Whatever you want to call it. It just makes it easier for me to remember the teams. So I can't remember who's in group 2, I can't remember who's in group 17, but I can remember who's in Justin for Taoiseach or whatever your name might be, okay? So please send me a name for your group, whatever it might be. It could be flippant, it could be a, you know, whatever name you want to call it. You can call it after your first pet if you want, or whatever you want to call it, okay. Let me see, I made a little... Bear with me for 10 seconds.
I hope so.
Okay, so for the benefit of our French students, put together a little PowerPoint show. Nice. Okay, so for French students, they want to know what Justin for Taoiseach means, the name of group number 2. Justin is a Turkey who started life on a children's TV program a long time ago. His full name is Justin Hoffman. He unofficially runs in our various elections here in Ireland, not as an official candidate, but as a kind of a protest vote. So every year he tends to poll several hundred, maybe even 1,000 votes, depending on how angry people are at the political situation. There he is there. The reason he is so popular in Ireland as a potential political candidate, and the reason why intelligent engineering students would rather, he was Taoiseach. Taoiseach, by the way, is the name we give to our Prime Minister. Taoiseach, it's an Irish word, it means chieftain. So the reason why intelligent people would rather this guy was our Prime Minister is because if you look at here's our present Prime Minister, here, pictured a few weeks ago. It's the guy here chasing a goose. Nobody quite understands. He was leading a delegation of European ministers in Ireland recently, and for some reason he put off and started chasing a goose on the field. So nobody quite knows. So this is the choice. It's either or this guy. This guy looks a bit, ineffectual. So why did we make him our Prime Minister? We made him our Prime Minister because this was the Prime Minister we had before then. You wonder, the French students, why did Ireland lose all our money? And this is the guy who lost all our money 4 years ago. Okay, so you can see compared to him, this guy is a good choice. And he was. So how did he become Prime Minister? He became Prime Minister because this was the guy we had before. This is our Prime Minister we had before. That guy, and he appeared in a TV advert hiding in a cupboard. Again, for reasons nobody quite understands. So that's a short little introduction to Irish politics. It's important for the French students while you're here. You're not just learning engineering, you're going to learn about the culture of Ireland as well and Irish society. Okay, so that's a little 30-second overview where we are. Okay, so Dustin for Taoiseach, this is Dustin. He's a better option than the people we have in place at the moment, fortunately. Okay, that's that. Okay, so that's all the announcements done. Please send me a name of your team, and please check this page here to make sure that your team name is included, okay? Because I will be using this to work off in terms of attendance and those kind of things. Okay, so let's go back to today's lecture. We've just logged in because I'll be doing some math hopefully later on. This is one of these 2-hour-long lectures, so we've got to take a break and do some math lab later on. Help ourselves from falling asleep. Okay. Which presenter that? Let's see. Oh, good. So, in today's class, I would like to talk about handout number 2. So again, apologies, I'm sort of jumping from handout to handout. The reason I'm doing that is because I want to cover handouts that enable you to do your assignment. Okay, this is a relatively standalone handout. You can do it without needing any of the other handouts. We can take it in isolation and we can cover it in isolation. And once we've covered it, it enables us to, enables you guys to do certainly handout, or certainly assignment number 1, the Newton-Raphson stuff. Okay? So we'll cover this now and we'll go back and we'll do handout number 1 probably on Friday. What's this all about? It's iterative methods for finding roots. So what does that mean? So what is a root? This is something you all know from a long time ago. What is a root? If we have a function f of x, a root is an input or such that it produces an output of 0. Okay, so in other words, a root is an input such that f of r is equal to 0. Very straightforward, you all know that. You've all known that for a long time. And there may be more than one root, in which case we can denote them, give them all a number, or 1, or 2, or 3 if as far as or n. Okay? There's a finite number of roots if as far as or n. There may well be an infinite number of roots, in which case we go R1, R2, ... keeps on going. Okay? So part of the problem in root finding can often be just number 1, finding out how many roots there are, let alone finding out what they are, even trying to work out how many roots we are looking for in the first place. Okay? So let's assume we know how many roots we're looking for, but we don't know what they are in this case. We need to find them. We need to find these values. Okay, so here's a little picture again, just to be absolutely explicit about what we're trying to do here. Here is a function. It's some generic function I've just scribbled down on PowerPoint. And it has, in this case, 5 roots visible with the little red dots. So they are the input, the x values such that the function evaluated at these inputs is equal to 0. Okay. In other words, it is where the function crosses the x-axis. And it's a well-defined problem to try and work out what these are. Okay? So you see some engineering examples of engineering situations where finding these roots enables you to solve some real-life engineering problems. Before we do that, let's just revise, more abstract functions that you're familiar with, and just revise or remind ourselves how to compute roots. So for a certain type of function, certain simple functions, we can work out roots analytically. So for example, a quadratic polynomial function, f of x, is equal to ax squared plus bx plus c, has up to 2 distinct roots. I say up to because it may have no roots, it may only have 1 root, but it has a maximum of 2 roots. So it doesn't have more than 2 roots. It may only have 1, or it may even have 0. It won't have any more than 2. And those 2 roots, I say 0 or 2, I'm assuming we're talking about real valued functions. Complex valued functions, a little bit more complicated. But for real valued functions, assuming real inputs, etc., we can have either 0 or 1 or 2 roots available. And in this case, for a quadratic polynomial, we can explicitly work out what these roots are. We can work out root number 1 is given in terms of these coefficients a, b, and c by a formula you all know, minus b plus root of b squared minus 4ac over 2a, and root number 2 is minus b minus root b squared minus 4ac all over 2a. So that's an example where we don't need a numerical root finding algorithm. We just use what we learned in school. Okay. Here's a simple case. Here is a function which, unlike the previous function, does not have a finite number of roots. The previous function only had a maximum of 2 roots. And this function here has an infinite number of potential roots. And these infinite number of roots occur at inputs x is equal to n times pi. Pi here being 180 degrees, or if we're measuring in radians, pi radians. Okay. So if x is equal to 0 or pi or 2 pi or 3 pi or minus 2 pi, etc., any integer value of pi, any integer multiple of pi rather, we get a root. Okay, that's for sine x. So if sine x has roots at an integer multiple of pi, how about sine of alpha x plus pi over 3? Where are its roots? Well, it's very easy to work out. We require that the argument here, alpha x plus pi over 3, is equal to n pi for some integer n. And just by rearranging that, we get alpha x equals n pi minus pi over 3. Therefore, x must be equal to n minus a third pi over alpha for integer values of n. Okay? So here's a function. Again, we don't need a numerical root finding algorithm for this because we know where the roots are. The roots occur at these points here. We can work it out. Okay. So you guys know all this. You're familiar with this, hopefully. And again, having learned all this in secondary school and in first and second year, you may have been lulled into a false sense of security such that pretty much every function you can find its roots using some kind of process. In actual fact, these are very much the exception. Most functions of interest to us as engineers are complicated things, and we don't explicitly know where the roots are. Okay? So these are rather exceptions. They're nice, they're simple, we can work out where the roots are. More generally, we don't know where the roots are. We need to have some sort of mechanism or algorithm to find them. So there's that in words. For most functions, it is impossible to find the roots exactly, and we must approximate. Now, how do we approximate them? Well, we're going to approximate them using an iteration method, by which I mean we're going to start with an initial guess, x0. That may be a good guess, it may be a very poor guess, and we're going to, in general, compute step-by-step approximations or updated approximations, x1, x2, until we get closer and closer to the root. Okay, so this is our broad strategy of what we're going to do. How we form an initial guess and how, more importantly, how we update it to get x1, x2 is going to determine whether it's a good route finding algorithm or a bad route finding algorithm. Okay, so this is a very general statement I've just made here. The devil is in the detail. Okay, when I say compute step-by-step approximations, or how do you do that? And how do you do it well? Another thing to note before we look at the detail of this is that for any given route finding algorithm that we come up with, we give it an initial guess x0. We may be successful. If we start with x0, we may end up finding a route, or we may not. If we do end up finding a route, we will have to run the algorithm again with a different initial guess in order to find the other routes. Okay, every function other than a linear polynomial will have more than one route, or has roots. And in order to find all of the routes, we need to run such an algorithm many times with many different initial guesses. Okay, so that's something else just to be aware of. Different initial guesses will lead to different routes. So let's do an engineering example, just again to motivate why this is useful. We discussed this last Tuesday, so I won't dwell on it too much. And we saw a similar picture on Friday when we were talking about random fading. So here's a picture of a concept known as ray tracing. So here we have a transmitter. A radio engineer has placed a transmitter here. He or she has a receiver placed here. And in addition to a line of sight path, occurring straight line path from the transmitter to the receiver, is a reflected path, hitting the ground at a certain point and arriving at the receiver. And we would like to know where this reflection point is, because where the reflection point is will determine how much energy gets reflected. Not all the energy that travels down here gets reflected. Some of it will get transmitted into the ground and get lost. Some of it will be reflected towards the receiver. And the amount that gets reflected depends on where this point is. Because it depends on where this point is, because that will determine what this angle is, and the reflection coefficient will in turn depend on this angle. So it's a useful thing and an important thing to know exactly where this reflection occurs. We'd like to know where it occurs. In this case, it's very easy to work out where the reflection occurs, because we can use a concept borrowed from optics called image theory. And what image theory does is it says, well, this is a big planar, and by planar I mean flat surface, a straight surface, and it's like a big mirror, okay, because we have something akin to a ray of light here, the radio wave, but at very high frequencies. It's similar to a ray of light. It travels in approximately straight lines. So it's like a ray of light. And what do we know about optics? Well, we know with optics, if a ray of light hits a mirror, we can trace it to its final destination by defining an image of the transmitter, the image of the object which produced the ray in the first place. And the image is just a similar distance, an equal distance away from this boundary as the actual transmitter is above here. So this distance, the transmitter's height above the plane, and this distance here, the image's height below the plane, is the same. Okay? And then what we can do is we can take this image and we can draw a straight line from the image to our final destination point, and where this straight line from the image to the receiver intersects our reflecting plane is where the reflection point is. So this construction is used a lot in optics, and we can use it here in situations where a radio engineer is trying to work out where a wave or a ray intersect with maybe a planar surface or the side of a building, something like that. However, not everything in optics and not everything in radio engineering is flat, like this. More generally, you might be interested in working out where a radio wave or a ray of light perhaps intersects and reflects from a curved surface. So here we have a curved surface in this slide, the blue semicircle here. And again, we have a similar setup. A radio engineer has set up a transmitter sending electromagnetic waves. We have a receiver here. This red dot is a receiver. And we would like to know, in addition to the line of sight path, which is a straight line from the transmitter to the receiver, whether there is a reflected path whereby a ray emanates from the transmitter, hits the semicircular reflecting object, and arrives back. We'd like to know whether such a reflection exists or not. Okay? Now, how do we know that such a reflection exists or not? Well, a reflection exists if we can find a point, a reflection point along this semicircle, such that when we draw the normal from that point out, well, a vector from the transmitter to the point and a vector from the point to the receiver will make these two angles, theta I and theta R, with the normal. Okay? And if we can find a point such that theta I equals theta R, that means the angle of incidence equals the angle of reflection. Well, by principle of optics, Fermat's principle, that is a reflection point. That's where reflections occur. Reflection points are marked out by those points where the angle of incidence equals the angle of reflection. It is not the case in the diagram I've drawn here. Here, theta R is very much greater than theta I, so this is not a candidate reflection point. But perhaps somewhere else along this semicircle, there is a point such that when we draw this little geometry, theta I and theta R will be the same. If we could find such a point, that's a reflection point. Okay. But the problem is, we don't know how to do that. If this was a planar geometry, we could do like we did, we could use image theory. This is not a planar geometry, so we have to solve it some other way. Okay. How do we solve it? Well, we can set up a function. We can define a function which is a function of phi. Well, what is phi? Phi is the angle from the origin here swept out by points as they move along this semicircle. Okay, so it's this angle here. Angle from the origin to the candidate point, the angle it makes with the x direction here is phi. So for points on the semicircle, phi varies from 0 at this extremity to 90 degrees or pi over 2 here to 180 degrees or pi radians here. So the location of all these potential reflection points is a function of phi. As phi varies, these points vary. And we can define another function of phi in the incident angle, a line from the transmitter to a point in the semicircle would make with the normal. That's the incident angle, theta I. That's a function of phi because as phi changes, the distance changes, and in turn, this angle, theta I, will change. And we can also define theta R, the reflection point, as phi changes along here, theta R will also change. Theta R is a function of phi, theta I is a function of phi, and we can define f to be the difference between these two angles. And if we do that, where we've explicitly written down expressions for theta I and theta R here, you can do that. F is of use to us because a reflection will occur when f phi is equal to 0. Because if we can find a value phi such that f phi is equal to 0, it means the right-hand side here is equal to 0, which means that theta I is equal to theta R, which means the angle of incidence equals the angle of reflection, which means we found a reflection point. Okay, so we'll do this example in MATLAB later on. Okay, we'll make a little bit of code to solve this problem. That's just trying to set it up. So at the moment what I'm trying to do is motivate the notion that in addition to quadratic polynomials and sinusoidal functions and cosines and logarithmic functions and simple functions that we've been dealing with to date, engineering is full of quite complicated functions for which we do not know how to find the roots, but we would like to find the roots, because if we can find the roots, we can do useful things like find out where reflections occur on a curved surface, for example. Okay. You all okay in NUIM over there? Let me know if there's any problems. Hopefully you can hear me. And send me some chat. Tell me you're still awake and still alive over there. Okay, let's keep on going. So the first thing we're going to do is derive a really simple but effective way of finding roots. A really simple way that everybody can do. Your granny could do this. Your granny can understand this. So let's consider a situation where we've got a little bit lucky. We have a little bit of prior information. We have a function f of x, and we do not know a root. We have not found a root of f of x yet, but we have found 2 points, a and b, that bracket a root. And what I mean by bracketing a root, I mean that either FA is negative and f of b is positive. In other words, f of a is below the x-axis, f of b is above the x-axis, or the other way around. F of a is positive and f of b is negative. So in both cases here, they bracket a root. In other words, if this is the case, there is a root somewhere between a and b. Okay? So both cases here are equivalent to saying that the product f of a multiplied by f of b is negative. Either this is negative and this is positive, or this is positive and this is negative. Either case, the product FA, FB is negative. So if we can find A and B such that the product FA, FB is negative, A and B bracket a root. Well, what do we mean by bracket? Let's examine case number 2. For case number 2, well, here's a function f of x. It has a root here at r. We found some value A, some input A such that FA is positive up here. We found some input B such that f of b is negative. Okay? And it so happens that if we can find such a case where one input is positive or has positive output, the other input has negative output, there must be a root somewhere between A and B. So if FA, FB is negative, in other words, one is above, one is below the x-axis, and f is continuous on AB, back in first year, the DCU people, we would have talked about continuity and what continuity means. Well, if f is continuous on AB, there must be a root somewhere between A and B. And why is that? Well, it's a consequence of a theorem that we're not going to prove, so I'm just going to flash it up here so that you're aware of it. The intermediate value theorem states the following. If f is a real valued continuous function defined on an interval AB, and u is some number between f of a and f of b, so f of a is some number, f of b is some number, u is somewhere in between the two of them, then there must be a c somewhere between a and b such that f of c is equal to u. And for a special case where c is equal to 0, in other words, this output that should say if u is equal to 0, that's a typo. In a special case where u is equal to 0, so u is a number between f of a and f of b. If u is equal to 0, we have a special case called the Bolzano theory. Bolzano was a Czech mathematician who discovered this way back in 1820 something. So this seems very obvious. Seems really obvious. You have, let's look at our picture again. We have a function. We have a function value which is positive. We have another input such that the function value is negative. It seems obvious there must be a root in between the two. It's continuous because the function starts up here at f of a, it finishes here at f of b. It must pass through all points in between. And if it must pass through all points in between, well, one of the points therefore it must pass through is 0. Just looking at it, that seems quite straightforward. And it is quite straightforward. It is as easy as that, but proving it is another matter. And we're not going to prove it. I'm just going to flash this theorem up. There is a proof. The proof isn't too hard. It uses concepts from real analysis and pure mathematics, concepts about completeness and continuity, some of which we covered in the first year, some of which we didn't. It's beyond our scope. This is the kind of stuff the mathematicians do. If you ever wondered, had you not embarked upon a career in engineering, if instead you'd studied mathematics, what would you be doing? Well, you'd be doing this kind of stuff. You'd be proving theorems like this. Theorems that appear to be very straightforward and appear to be very obvious until you actually try and write down a rigorous proof. When you write down a rigorous proof, you realize it's not that obvious. Okay, you've got to be very careful how you define things. Okay, so we're not going to look at the proof. You can find it on the internet. If you're very interested, you can find it on the internet. It's beyond our scope. But I just flash it up here just to give you a little bit of context of the kind of thing mathematicians do all day long for kids. Good. So let's get back to our bisection algorithm. We have found by the intermediate value theorem, or Bolzano's theorem, tells us that if you can find A and B such that A and B bracket a root, in other words, f of A is positive and f of B is negative, or the other way around, there must be a root somewhere between A and B. What do you do? A isn't a root, B isn't a root. How do you guess where the root might be? Any suggestions what you might do? The average, yeah, it's a good idea. We don't know, in this particular case, we know where the root is because I've drawn you a picture, but in general, we don't know the shape of this function, and we certainly don't know where R is. All we know is that A and B have a root somewhere in between them. So if we don't know where in between them it is, it makes sense that what we should do is we should choose the midpoint.
Connor?
Hello, how are you?
Looks like, yeah, looks like people have dropped, so I was disconnected and a few other people might have. Looks like they have dropped from 15 to 11.
We're back up to 13, so I'll just wait for a minute, okay? And then I'll kick off again and we get back up. Yeah. Thanks, Paula.
Cheers.
Okay, we've lost one or two people in the news, so just while they're logging in again, we'll just take a little break, just for 1 minute. Okay, so I think people are back again in NUIM, so we can resume. So, just to recap, we're trying to find a root. We have a function. We don't know where the root is, but we have been fortunate enough to find A and B such that we're confident there is a root somewhere between A and B. We don't know where it is, somewhere between A and B. So, well, in the absence of any other guesses, what we should do is we should take the midpoint. Let's take A plus B over 2, which is halfway between A and B. So what does the bisection algorithm tell us to do next? Well, we take this midpoint C, which is halfway between the two, and we ask the question, is when we feed C into the function f, we get output f of C. Is that output positive or is it negative? In the picture we have here on the screen, we have f of C is negative. Okay. So what does that tell us? We had a situation where the root was somewhere between A and B because f of A was positive and f of B was negative. Now we can conclude that the root is somewhere between A and C because f of A is positive and f of C is negative. In other words, we can replace B with C. Okay? So now we started off with a root somewhere between here, A and B, and now by analyzing f of c, we know there's a root somewhere between a and c. So there are two possibilities in general. Having found c, which is halfway between a and b, either a and c now bracket a root. In other words, fa times fc is negative. Fa is positive, fc is negative, or the other way around. In which case, you can replace b by c, which is the case we had a picture just a second ago. Or alternatively, c and b bracket a root, in which case the product of fb and fc is negative, in which case we can replace a by c and repeat the process. Okay, so either this happens or this happens. We started off with the root somewhere between a and b. We take the midpoint, and either one of two cases happens. Either the root is now between a and c, or it's between b and c. Okay? And we half the interval accordingly. We do a little bit of MATLAB check. We see which of these two cases holds, and we replace either a or b accordingly. So in our case, we had the first scenario, fa, fc was negative, so c becomes the new b. So b was here, over here somewhere, and becomes this one. Now we have a smaller interval, ab. And we repeat the process again. Just keep on going. So again, we define a midpoint, a plus b over 2. And we get c here, this particular example I'm looking at. In this case, we now have f of a is positive, f of c is positive, f of b is negative. That means there must be a root between c and b, because the product fb and fc is negative, f of b is negative, f of c is positive, so the root must lie between c and b. So in this case, we replace a with c, and our interval halves in size again. And this is what we get. So we had an interval of a certain size, we halved it, and we halved it. And each time, our interval is getting smaller, and the midpoint of that interval, which is our estimate for the root, is getting closer and closer to the real root. Okay. And we just continue. We keep on doing this over and over again. Here's our new estimate for C, and so on. Okay, and we continue. We're happy that we've got something which is close to a root. How do we know it's close to a root? Because once we get to a situation where f of c is very, very small, less than some threshold that we define in advance, we have some threshold, maybe 0.00001. Once we find f of c having absolute value less than that threshold, we say we're close enough to a root. We will never find a situation where f of c is equal to 0. The best we're going to do is get f of c being very, very, very small, smaller than a predetermined threshold, at which point we terminate the algorithm and say our estimate for the root is c. Okay. So we can write the algorithm as follows. We start off with a function, f of x, and a threshold. This is our accuracy threshold. What we're trying to do in the algorithm is find the root of the function f of x. To initialize our bisection algorithm, we choose initial points a and b that bracket the root. In other words, f of a times f of b is negative, and we choose the midpoint, a plus b over 2. And then to code up this algorithm, the main iteration is that, well, while the function value at the midpoint has absolute value greater than the threshold, do these logical steps here. If a and c bracket a root, then, if a and c have the same sign, in other words, if they're both positive or both negative, then replace a with c, otherwise replace b with c. And then make our new interval ab and make our new midpoint c, and keep on looping around this while loop until we find a value of c that satisfies this criterion here. Okay. Very, very simple. Many lines of code, 8 lines of code, very robust. It'll always work. It'll always find your root. Okay. People, any questions about that as an algorithm? It's very, very simple. You can explain this to your granny and she can code it up in Java for you. It's that easy to do, okay? Has anybody got any observations about this as an algorithm? Do you think this is a good algorithm? No? Any? Oh, does it work for complex? That's a good point. Only works for real numbers, because complex numbers, the concept of bracketing a root only really works for real numbers. The concept of bracketing a root only works for real numbers. In complex numbers, we can define a disk within which the root lies. But then, what would you do? Here, give an interval. Okay, so it's a simple straight line made to be. Okay? It's a good question. Any other queries or comments about the bisection method? It's very robust. It will generally work. It will generally find you a root, provided you're going to wait a long time. Let's have a look at this step here and see something very foolish that it is. For example, it's quite unintelligent, use much intelligence. At this point in our algorithm, we have A and B bracketing a root, and we had our estimate C here, which is actually very close to the root as it transpired. We didn't know that because when we're applying this algorithm, we don't know where the root is, but in this particular case, it was quite close. When we applied the algorithm again, or the iteration again, A became this value here. Okay, A here, and our new midpoint became this value here. So we actually ended up going away from the root. So this particular step was actually a little bit of a retrograde step. It went a little bit backwards. We started off with this point quite close to R, and then because the algorithm is quite blind, doesn't inject much intelligence, our next value that we got was here, which is actually further away from the root than we were. Now it will correct that because the next value again, so it stops there, but had we kept on going, it would rectify and we'd eventually get arbitrarily close to R. But for any given iteration, it's not very clever. It just does the same thing over and over again. Okay? So it's a bit of a workhorse. It does work, works very well, it's robust, but it's not very intelligent. Sometimes it does backward steps like that, almost, but we'll eventually get there in the end. Okay. Any other queries about it? It generally works. If you can find A and B that bracket a root and apply this algorithm, it will find you the root. In contrast to other algorithms that we'll define now in a second. Hey Manuth, how are you getting on over there? Have you any queries for me or any questions? I see one or two people dropping out an audio. Hopefully you were able to hear all that. If you have any questions, please send me a text. Any questions about the bisection algorithm? Okay, well, we'll keep on going in the absence of questions. In. A very good question. Okay. So the question here, NUIM, it's a good question, is if there were two roots in the interval AB, how could we tell or what could we do? Anybody want to try and answer that? Could there be two roots between A and B? Okay. Exactly. Yeah. If there was two roots between A and B, you'd have two zero crossings, and we would have FA and FB would either be both positive or both negative. Your question is still a good one because the situation would be, could be, so in terms of our little rule, so we start off by bracketing an interval, and we say that it brackets a root provided that f of A, f of B, where's it gone? Way back then. We say that this means it brackets a root. F of A, f of B, negative, means it brackets a root. In actual fact, I'm being a little bit loose there. Could somebody tell me what f of A f of b less than 0 actually means. You're welcome to throw in a guess. So here I've said f of a, f of b less than 0 means that there is a root between a and b. In actual fact, we can loosen that a little bit more.
One has to be negative, is it?
No, well, if f of a, f of b is negative, it means that it has to be negative. So you're right in saying that. But Connor in NUIM has a good answer. Connor in NUIM has noticed if a, fb is less than 0, it means that the function must cross the x-axis an odd number of times between a and b. It crosses an odd number of times. It means it crosses the x-axis once, or 3 times, or 5 times, or 7 times, and so on. Okay. So it means there is either a single root in there, or maybe 3 roots, or maybe 5 roots. So it can't be 2 roots, as we pointed out. If there's 2 roots, FA, FB would be positive, or yeah, it would probably be positive. So what this actually means is you can have either 1 root or 3 roots or 5 roots. But the bisection method doesn't care. It'll find one of those roots, be there 1 or be there 3 or be there 5. But the danger is you could apply the bisection method to a situation like this. You could find a root and conclude that you have found all of the roots in that interval. When in actual fact, you may only have found 1 of 3 or 1 of 5 or 1 of 7. So it's a little bit of a drawback. You've got to be a little bit careful about how you apply the bisection method, because if this interval AB is very, very, very long, and you have this criteria holds, and then you've got to be a little bit suspicious that maybe there isn't just a single root, there may be many roots. So ideally, we would like this criterion to hold and the interval AB to be quite small. The interval AB is quite small. Chances are there's only a single root. You don't have 3 or 5 or 7. Okay, so well done, Connor. It was a good answer. It's a good question in the first place. So that's the bisection algorithm. It's very robust, but again, nothing is ever easy. There's always drawbacks to it. So it's robust, but it's kind of slow, and you're not guaranteed to find all the roots. And also you can miss. When you're trying to find your initial interval A and B, actually, you know, how you do that, I haven't discussed. You have to come up with some way of doing that. And you could easily have trial intervals, and those trial intervals may actually contain 2 roots. And you may dismiss that interval as a consequence, and you may miss those roots altogether. So there's implementation aspects that I haven't covered here, but you need to think about it a little bit. Okay, so let's do something better. That's the bisection algorithm. It's good, it's very reliable, but it's a bit slow. Can we do something a little bit more clever by having a more intelligent algorithm? You guys are intelligent. Let's do something intelligent. And let's do what is called the input-output approach. So this is a kind of a general approach. We'll start off with a general definition of an input-output method, and then we'll come up with what's called the Newton-Raphson method, which is the Newton-Raphson method, which is a special case of an input-output method. So an input-output method, here's the algorithm. We have some constant or some number beta, some function f of x, some threshold delta. Actually, I'm a little bit loose here. This beta isn't actually a constant. Beta changes from step to step, so I shouldn't really call beta a constant here, so as we'll see later on, okay? So beta is just some number or some variable. We shouldn't really define it as being a constant, it's a variable. With a function f, we're trying to find its root, and we have a threshold. Again, we have a threshold because this is a numerical process. We're not going to find a root, but we are going to find some number such that f of that number is less than the threshold. So the result is to find the root. We initialize by choosing an initial guess x0. So we just have a single number. We don't start off by bracketing a root as before. We just start off with a guess, x0, picked at random if needs be. While f of xn is greater than the threshold, in other words, our latest estimate is most definitely not a root because its function value is very much greater than 0, you do the following. You take your previous estimate xn and you update it to make xn plus 1. And you update it by taking the previous guess xn, working out f of xn and scaling that by beta. Okay, so the new guess is equal to the old guess plus the function evaluated at the old guess multiplied by beta. That's a general family of methods called the input-output method. Okay, and some of these work, some of these don't work. So let's try and work out why it may work, or indeed why it may not work. So it's going to converge, it's going to give us a good answer in the situation where f of xn gets closer and closer to 0, i.e. xn gets closer and closer to a root. If f of xn gets closer and closer to 0, this term here will get very, very small, and we'll find xn plus 1 gets very close to xn, because this update will be very small, because f of xn will be very close to 0. So it will converge when x of n plus 1 is equal to the previous update, so it's no longer updating, the updates are minimal. And that can only happen provided this term is equal to 0, in other words, xn is a root. Okay. Now, some caveats about this. If the process converges to a steady xn plus 1 value, so it stops updating, then we found a root. But that's an if, because it may not converge. It may keep on going forever. There's no guarantee. This algorithm is not as dependable as the bisection algorithm. The bisection algorithm is a bit stupid, but it's kind of honest and it keeps on plowing ahead. It can get you an answer. This one here will go crazy on you. It could give you a crazy answer altogether. So it'll be a little bit more careful. So if the process converges, it's not entirely clear whether it will or not, and we'll investigate that later. However, the process may not converge to the root we want. We may be looking for a particular root. This process might converge to a completely different root, and it may not converge at all. So obviously, whether this whole process works or doesn't work depends entirely on this parameter beta. Beta is this scaling factor. Let's just look at our algorithm again here. So to update our guess, we take our previous guess, we take the function evaluated at our previous guess, and we scale it by beta. So we need to pick a good value of beta. You can pick a good value of beta, this would be a good algorithm. Pick a bad value of beta, this is a bad algorithm. So how do you pick a good value of beta? So you guys are engineers, you're in third year, you should be beyond just blindly guessing values for beta. You can try that if you want. You can hold this algorithm up, you can put in random values of beta, see what happens. It's not a very good approach. What we're going to do is do some mathematics to try and derive a good value of beta, a sensible value of beta. So what do we do? Let's do a little bit of what's called error analysis. So let's look at the error in our process and try and work out how can we control the error. So let's imagine we've been doing this algorithm for a while, and we are now at iteration n, and our estimate is given by xn. And xn is equal to the root plus some error, epsilon n. Okay? We don't know what the root is, and we don't know what the error is. We don't know either of these, but we know the sum of them together is equal to xn. So we know what xn is, it's our present guess, and we know what our present guess can be expressed as the actual thing we want, the actual answer, plus some error. We don't know either of these two things. Let's make life a little bit easier for ourselves. Let's imagine we've been lucky thus far, and our n estimate is kind of close to the root. So epsilon n is kind of small. Okay, so let's imagine this is pretty small, just to make this analysis a little bit easier. So let's put this expression, this error expression, into our iteration process. And the iteration process says, well, if this was x of n plus 1 is equal to x of n plus beta times f of x of n. This is going to be our new estimate. And what we would like to do is work out a new estimate, or choose beta, such that our new estimate has an error which is smaller than our previous estimate. If we can make a new estimate which has a smaller error than our previous error, then we're doing good. We're making the error smaller. So we would like to choose beta such that the error associated with this estimate is smaller than this. How do we do that? What can we say about this here? Beta, or f applied to xn, or f applied to the root plus epsilon. Can we say anything about this? Can we manipulate this in any way? Well, we can. Let's remind ourselves of some stuff we learned previously in mathematics. We learned about the Taylor series and we learned about the Maclaurin series. So the Maclaurin series is a way of taking a general function f of x, and writing it in terms of a polynomial. So here is a general function f of x. It could be an exponential function, it could be a sine function, it could be any function whatsoever. It is possible to write that as a constant, which is the function value at 0, plus x times the first derivative at 0, plus x squared over 2 times the second derivative evaluated at 0, and so on and so on and so on. And the more terms we take here, the larger degree of this polynomial, because this is a polynomial, it's a terms in x, x squared, x cubed, x to the 4, etc., all of which have these constant coefficients. So this is a polynomial. So we're approximating something which isn't a polynomial, we're approximating it as a polynomial. And the more terms we take, the better this estimate is. Okay, this is called the Maclaurin series. More generally, you can write a Taylor series, which is like a Maclaurin series, but rather than expanding around x equals 0, we expand around a general point x equals a. And a Taylor series does the same thing. It takes a function, some potentially complicated function, and writes it as polynomial. So it writes it as the function value evaluated at this point a, plus x minus a times the first derivative at a, plus x minus a squared over 2 times the second derivative at a, plus dot, 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 all of these terms. Okay. And again, this is a polynomial. There's a constant term, there's a term here in x, there's a term here in x squared, etc. And the larger the number of terms we keep in this polynomial, the closer this polynomial resembles the actual function. This is called a Taylor series. And it's hugely important because it means you can take an arbitrary function and you can express it in terms of a polynomial. And polynomials are nice because they're easy to work with. And we like polynomials because we understand them. Okay? So here's a potentially complicated function being replaced to arbitrary accuracy with a nice function, a polynomial function. And a, this point here is called the expansion point. Okay, so let's do a quick example, again, just to remind ourselves what a Taylor series is. So let's consider the function f of x is equal to e to the power of x over 2, e to the x over 2. And let's compute a Taylor series for this function. So this is a function. It is not a polynomial. Most definitely is not a polynomial, but we can approximate it by a polynomial. So let's assume the expansion point a is equal to 1. So if a is equal to 1, well, our little recipe says we have to work out the function value at a, which will be e to the power of 1 over 2, e to the half, which is roughly that. We have to work out the first derivative evaluated at a. Well, the first derivative will be a half e to the x over 2, evaluated at x equals 1. We get that. We've got to work out the second derivative at x equals a, which when you work it out, you get that. We've got to work out the third derivative, you get that, and so on. Okay, so higher order derivatives, you can work them all out. And then you put them into the expression. We can say a third order Taylor polynomial approximation to this function. This function is not a polynomial, but this is a polynomial approximation to it, is obtained by taking these numbers here and using them as coefficients in this expansion. So we get f of a, which is this number here, plus x minus a times this number here, plus x minus a, which is x minus 1, because we're assuming a is equal to 1, x minus 1 squared over 2 times this number, plus x minus 1 cubed over 6 times this number. And this is just a polynomial. You can expand that out, you'll get a constant term, an x squared term, an x cubed term. Okay, and you can simplify it, that's what you get. You can simplify it a little bit more, and that's what you get. Okay. And, well, here's what you get if you plot these, this approximation. The black curve here, you can barely see it, apologies, I'll try and maybe get a better picture of this and put it in the notes. But there's a black curve here, which is the actual function, e to the power of x over 2. Okay, now the red curve and the green curve and the light blue curve and the yellow curve are varying polynomial approximations. If we only take the first term in this expression here, f of a, we get a really bad approximation. We get this curve here, the red line, which is nothing like the black line, particularly. If instead we take the first two terms, so this term plus this term, we get the green line. It's a linear approximation to our underlying black curve here. Okay? It's a little bit better, still not great. If instead we retain three terms, so this term plus this term plus this term, we get a quadratic polynomial approximation, which is the light blue approximation here, which tracks the black curve pretty well in this region. And instead, if we retain all four terms, 1 plus 2 plus 3 plus 4, all of these terms taken together gives us a cubic polynomial, which is the yellow curve here. And we see the cubic polynomial tracks the function e to the x over 2, the best of all of them. Okay? So by taking more and more terms here, we could add in more terms if we wanted to. There's an infinite number of terms we could potentially add in. The more terms we add in, we go from a pretty poor approximation to a linear approximation to a quadratic to a cubic. Each time we're getting closer and closer to the actual function we're trying to model. Okay. And we can keep on doing this. We could make it a polynomial of degree 4 or 5 or 6 or 7, and each time we get a better fit. What we see in all cases is that regardless of the degree of the approximation, it's always exact at the expansion point, a equals 1. So they all agree at this point. They all cross over at this point and give the correct answer for this input. And in the immediate vicinity of the expansion point, 1 plus or minus a little bit is where they are all most accurate. So they're all pretty good around the expansion point. They get worse the further away you go. And the approximation is better the higher order degree you keep. The yellow one here, the cubic polynomial, is better than the constant polynomial. Okay. Just a little bit of revision about Taylor series, okay? Because we're going to use a Taylor series. We're talking about an input-output algorithm for root finding, and we're going to use this Taylor series in order to make a good choice for beta. So we just wanted to revise Taylor series. Has anybody got a question about Taylor series at this point? We've all seen this before. You know all this stuff. Okay. So how can we use this? Well, an alternative way of writing the Taylor expansion is rather than writing in terms of f of x, where x is some unknown, we can say x is some variable. It's equal to the expansion point plus h, in which case then h is equal to x minus a. And the expression we had, f of x is equal to blah, 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 blah. When you make this substitution, just becomes this instead. So this is exactly the same information, just expressed in a slightly different way. Okay. Now, let's look at let's go back a few slides just very temporarily to see where we stopped talking about our input-output. In our input-output algorithm, we had got to this point here. Where are we? Here it is. This is where we got to. And we wanted to see, well, what can we say about f of or plus epsilon? Can we do something with this? Turns out we can. Because here's our Taylor series. Animations. Yes. See now this. Okay. Well, we've seen. We'd like to be able to say something about f of or plus epsilon n. Well, f of or plus epsilon n is something of this form. And we can therefore expand it using a Taylor series. So if f of a plus h can be expressed as this, f of or plus epsilon can be written as f of or plus epsilon times the first derivative at or plus epsilon squared over n multiplied by the second derivative at or plus etc. So this is just this expression, the Taylor series, with a is equal to or and h is equal to epsilon. And what we can do is we can say this is an infinite number of terms here. The plus dot 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 here means it goes on forever and ever and ever. What we'll do is we'll arrange them in order of importance. We're assuming epsilon n is a small number. So let's imagine epsilon n is 0.1. It's a pretty small number. Well, if epsilon n is 0.1, epsilon n squared is 0.01, which is a very small number. Epsilon n cubed is 0.1 cubed, which is a really small number. Epsilon n to the 4 is a really small number, and so forth. Okay? So if epsilon n is small, these terms are getting smaller and smaller and smaller and smaller and smaller the further out we go, which means that the most important terms are over towards the left. These are the important terms, and over here to the right are the less important terms. So we introduce some notation, this order epsilon n squared. This notation here means that we've taken all terms which have epsilon n to the power of 2 or greater, so epsilon n to the 2 or epsilon n to the 3 or epsilon n to the 4, taking them all together and just thrown them into a big bucket together, and we call that big bucket order epsilon n squared. Because all of these terms are really small, and we assume that this is the most important one of them, because the terms get smaller as you go to the right. So here's an infinite number of terms, and the most important one is some constant multiplied by epsilon n squared. Okay. People happy with that idea? So we have a small number of epsilon n, which means that of all this infinite number of terms here, this first term is the most important. It's pretty small, but it's less small than all these other guys. These other guys are tiny compared to him. So we put them all together in a bag, and we call that bag order n squared, or order epsilon n squared. It means that everything in here is either epsilon n squared or smaller. An important notation. We'll be using it a lot. The reason you have that notation, it just makes life easier. You can take a whole bunch of terms and just turn them into a single term in a sort of a hand-wavy, approximate sort of way. So, includes all these remaining terms, and the notation suggests that the largest of these terms is this one here, which is of the form epsilon n squared multiplied by some constant, alpha. So, now what can we do? Our update was the following. This is our input-output algorithm. We're trying to find a good value of beta. Remember, this is what we're trying to achieve. And we had xn plus 1 was equal to or plus epsilon n plus beta times f of or plus epsilon n. Well, f of or plus epsilon n, we have just written, can be written as this thing here. If we take this here and put it in, this is what we get. Okay. So we've learned something. We're trying to find the value of beta such that our new estimate will have a smaller error than our previous estimate. So our new estimate, xn plus 1, is equal to our answer, or plus this expression here, which is the new error effectively, and a whole bunch of little small things we're going to ignore. So this here is effectively the new error after a step. So provided that 1 plus beta, f dash of r is less than 1, this product will be less than epsilon n and will have reduced the error. So at step n, the error was epsilon n. At step n plus 1, the error is epsilon n multiplied by this. If we can make this thing less than 1, we reduce the error. So provided this is less than 1, we can reduce the error. Okay. We've done some Taylor series expansions, and we've made a little bit of progress with our problem. We still have a problem. So we've discovered a good choice of beta will be a value of beta to make this thing less than 1. We have a problem because we don't know what this is. We don't know what or is. So we don't know what value of beta we got to choose in order to make this less than 1 because we don't know f dash of r. We've made some progress, but not enough. We've got to do a little bit more. So what else can we do? What we can do is we can assume that epsilon n is small. In other words, we're pretty close to where we want to be. And we apply Taylor series again. Let's take f dash of r. We don't know what f dash of r is, but let's try and approximate it. Well, we know that r is equal to our previous guess minus the error. because we defined x of n as being r plus epsilon n, so r is equal to this. So we don't know f dash of r, but we can write it as f dash of a previous guess minus the previous error. And we can expand that with a Taylor's expansion. This is a function, f dash, evaluated at xn minus epsilon n, and by the rules of the Taylor's expansion, we can write that as f dash evaluated at xn minus this little increment here, epsilon n, times the first derivative of this, which will be f double dash, evaluated at xn, plus a whole bunch of extra terms, an infinite number of extra terms which are pretty small, and we're going to ignore them. They're of order epsilon n squared or smaller. So we'll put them all in this bag and label it order epsilon n squared so we can ignore it. Well now, how does this help us? A lot. Because this is what we had. Our new estimate, xn plus 1, was equal to the root that we wanted, plus the previous error multiplied by 1 plus beta f dash r. And we wanted to choose beta to make this really small. But we couldn't because we didn't know, we had no information about f dash r. But now we can approximate f dash r in this fashion. We can throw this thing here. When we do that, we take this expression here and we replace f dash r with this. We just tidy it up. We have order epsilon squared here. We've got epsilon n times epsilon n. This gives us epsilon n squared times this. We've got order epsilon n squared times epsilon n beta. All of these things here are small. They're all of order epsilon n squared or smaller. So again, we needn't worry too much about the details. We recognize that they're all very small. They're epsilon n squared or smaller, and we'll just group them all together using this curly O notation. So this curly O notation is great. It means you don't have to worry too much about the details. You're just confident that these are all very small numbers, no greater than epsilon n squared. And we just group them all together and concentrate on what's happening over here. What's happening over here is great because we had a situation where we had to choose beta to make this small. We couldn't do that because we didn't know what r was. But now we have a situation where we can choose beta to make this small. And we can do that because we know what this number is. This number is 1. And this is f dash at xn. And we know what xn is. So in particular, well, what is a good choice of beta? Would anyone care to volunteer a good choice of beta? We want to make this as small as possible. This thing here in the brackets. Anybody in NUIM want to volunteer a good choice of beta? How can we make this thing in the brackets as small as possible? Yeah, you can make what's in the brackets equal to 0. Exactly. So how can we make what's in the brackets equal to 0? We can make what's in the brackets equal to 0 by choosing beta equals minus 1 divided by f dash at xn. And we can do that because we know xn, it's our previous guess. We know f, it's the function we're working with. Therefore, we know f dash because we can just differentiate it. So we know all these quantities. So we can make beta equals minus 1 over f dash xn. And if we do that, this whole thing in the bracket goes to 0. Which means that our new estimate, xn plus 1, is equal to the desired root plus 0 plus a whole bunch of small little terms which are epsilon n squared. So in the previous step, at xn, the error was equal to epsilon n. And now at xn plus 1, the error is epsilon n squared, which is much, much smaller. Wow, someone's head exploded in the news. Someone just got so freaked out by that result. Is everybody okay in Maynooth? We heard a very strange noise. Someone sneezed maybe. I'll mute you all again. All okay. Thank you, Kieran. So let's recap on why this is so exciting. This is so exciting. This is so exciting because we had at our previous estimate, we had xn. It had an error epsilon n, which was a small number. By doing this process and by using this choice of beta, at the next step, xn plus 1, the error won't be epsilon n, it's going to be epsilon n squared. And if epsilon n is small, epsilon n is 0.1, epsilon n squared is much smaller. And we're squaring the error at every step. So it means once we get close to the root, doing this process is going to be really good because it's going to accelerate towards the root very, very quickly. Okay. So this yields the following Newton method or Newton-Raphson method. So we said on Friday that we had 100 slides and you guys just had to stay awake for one slide. Similarly here, this is the one slide you need to stay awake for. This is the one thing you need in order to do your assignment. Well, you need more than this, but this is the guts of your assignment. The Newton-Raphson method is really simple. The Newton-Raphson method takes an initial guess, x0, and then it updates x1, x2, x3, x4, etc. according to this rule. Xn plus 1 is equal to the previous estimate, xn, minus beta times fxn, where beta is minus 1 over f dash xn. So the reason we did all this painful mathematics for the last number of slides is because, again, you guys are engineers. And I said last Tuesday, as part of this course, I could walk in here and I could put this up on the blackboard and we'd be finished in 5 minutes. And you guys are clever. You could implement this and you could do it. And your life would probably be, you know, unremarkable. This would work most of the time. The reason we need to do all this stuff, because as engineers, you guys need to know why this is how it is. It's not enough just knowing this and being able to implement it. You need to know why this particular choice of update is a good choice. And it's a good choice because as our error analysis shows, it will make the error square every time. And if the error is small, squaring the error is a good thing to do because squaring a small number makes it smaller and smaller and smaller. Okay, so this is Newton-Raphson algorithm. This is several lines of MATLAB to code, very easy to code, but the hard part is understanding it and why it is the way it is. Let's see it in action. Let's do an example. Here's an example. We don't even need a computer to do this. We can work it out by hand. Let's take the Newton-Raphson method and use it to find the square root of x of a given, the square root x of a given positive number. So apply it to c is equal to 2. So in other words, get the square root of it. So let's make a function f of x equals x squared minus c. This will have a root when x squared equals c, or in other words, x is equal to the square root of c. Okay. Its first derivative, because we need to know the first derivative of it in order to apply Newton-Raphson. Newton-Raphson requires that we're able to work out first derivatives here. So the first derivative of this function is equal to 2x minus 0 at 2x. So the Newton-Raphson formula takes the form xn plus 1 is equal to xn minus f of xn, which is x squared n minus c, divided by 2xn. And you can simplify that a little bit. You could get this, cancels out a little bit. That's what you get. And we were asked, for the particular case of c is equal to 2, use this iteration to work out the square root of 2. So if you do it, we can start off with our initial guess of 1. 1 is most definitely not the square root of 2. So x0 is equal to 1, but by applying this process, we can get x1, we can get x2, x3, x4. And what we see is the following. x0 is 1, that's our initial guess. No, it's probably here, so almost finished, so should be okay. When you do this, our first estimate is going to be a half times 1 plus 2 over 1. That's equal to 1 plus 2 is 3, and a half of 3 is 1.5. So if x0 is 1, x1 is going to be 1.5. You do it again, you put 1.5 in, work it out again, you get this, you get this, you get this. And we can see we're getting closer and closer to the actual answer of the square root of 2, which is 1.414213, blah, blah, blah. But you can see here the error is Very, very small. So even after 1, 2, 3, 4, 5, or 4 iterations, an initial guess and 4 updates, we have it right to about 10 or 12 decimal places. This is really fast. This is really fast convergence to the root. Okay. And another thing we should notice is that we would expect the error at iteration n to be equal to the error at the previous iteration squared times some constant. Because remember, what our error analysis suggested that the update gives us an error which is equal to the previous error squared multiplied by some constant. So we should find that the error at step n divided by the error squared at the previous step should converge to some kind of constant as it goes on. And we see that this is the case. It gets closer and closer to 0.353 or so. So this is showing that the error, as the error gets small, we have this behavior as predicted, that the error at the nth step is equal to the error at the previous step squared and multiplied by a constant, which is about this. Okay. People are tired. You tired, Manuth? Tired here, you should see them. And our computer is tired. The computer's just run out of electricity, so we'll leave it there. Thanks for your attention. There'll be a lecture on Friday at 2 o'clock. NUIM people, you can contact me by email if you want to talk to me by Skype or by phone on Friday. I'm available for an hour, so you can make use of that resource if you want, okay? So have a good week, and I shall see you all on, well, I'll see you virtually on Friday, okay?